Hello folks, Dynodon here from Shaver Racing Engines, and today I'm going to talk just a tiny bit about cooling systems for one of our sprint car engines. Now, I had a hard time figuring out how I was going to do this because different engines require different things to do with the cooling system. Ford's quite a bit different than Chevrolet, but mainly most of the people that are racing Chevrolets, and the different divisions also require different types of cooling systems. But today I'm just going to focus on what we're doing with the Chevrolet sprint car engine. Quite a long time ago, Ron Shaver and a number of other people figured out that the cooling system for the standard cooling system for a Chevrolet was not adequate enough to keep an 800 or 700 or 900 horsepower, now 960 or 70 horsepower engine cooled. So what they did, what we figured out quite a long time ago, is that one of the problems with a Chevrolet is that the hottest part of the engine is right in between the two exhaust valves. That's the hottest spot in the cylinder head. So one of the things that we did to correct that problem, or try to solve the problem of getting that part of the cylinder head too hot, because when it does get too hot, it has a tendency to lift the cylinder head right there and it blows the gasket in between those two cylinders. So what we've done is we've taken on the sprint car engine, the water pump's driven off the crankshaft right here, which you can probably see. It's not really that great of a picture, but we're basically reverse cooling the engine, and what that means is that we're not putting the water in from the water pump directly into the block anymore. We're taking the water from the water pump and we're running a hose, in this case the Dash 16 hose, directly into the cylinder head, right into the middle of the cylinder head between the two exhaust valves where it's the hottest part of the engine. This part of the engine gets cooled down quick, so the temperature inside the head is much more even, and the tendency to blow a head gasket is a lot less. So the water goes into the head, into the middle here. It travels from the center out to the ends of the head, goes down into the block. And if you can see down here, it's kind of a bad picture, but if you can see down here, there's two openings here in the block here, on either side of the center, that the water comes out at. So we've got a Dash 16 line going in. We've got two Dash 16 lines going in, two Dash 10 lines coming out. And also, too, if you can see here, right on the very top, we've got some very small hoses on the top of the cylinder head here, which are bleeds. They bleed all the air out of the system, and they don't flow a ton of water, but they do bleed a little bit of air out of the system and keeps the air out of the system, because one of the biggest issues that we have with cooling is hot spots in the cylinder head. Every cylinder head, when it's running, is going to get hot enough that there will be spots inside the cylinder head that will boil. And when that happens, we have to get that air, that boiling air, out of the system as quickly as possible. And that's what these little lines are for. They go back to the radiator and they deposit all that air in there. So if we can keep air as the water temperature goes up and it starts to boil, we try to get that air out as soon as possible. Also, too, one of the big things that's very, very important, I was just talking with a good friend of mine, Russell Blinas from GM Racing. He's the head of GM Powertrain. I've done a number of projects for him, and we're both in agreement that one of the biggest issues with water going into an engine is the amount of flow here. We are one of the few shops that can actually measure the flow of water going through an engine, and we have all come to the conclusion that the more flow you've got in an engine is better, and there's a couple of reasons for that. One, because this water pump is capable of, in this particular configuration, this water pump is capable of about 70 to 80 gallons per minute, which is quite a bit. Standard rule of thumb, 10 gallons per minute per 100 horsepower. So if you've got an 80 horsepower motor, if you flow 80 gallons a minute, you can probably keep it cool. But the other thing is when you've got a water pump that's actually flowing more water than the engine's capable of taking, the pressure inside the engine goes up. For example, this particular setup, the way we have it with two Dash 16s going in and two Dash 10s coming out, this motor will flow about 70 gallons per minute, this particular one here. Because of that, the pressure inside the engine, will go anywhere from 60 to 70 psi. So when you increase the pressure, the water pressure in the motor, you're also increasing the boiling point of the coolant you have running through it, which decreases the amount of air bubbles that actually form inside the engine, thus creating more space for the water to take the heat out of the engine and transfer it back to the radiator. That's today's tech tip.